Okay. Good afternoon, dear conference participants. Good afternoon, everyone. Today, my name is Maxim, and I want to present you current result of the study of our research group in the field of automatic post-processing of the yarn data. It sounds complicated, but we'll deal with it. So, as we all know, that WordNet and Thesauri are considered to be one of the most important tools in the hand of the researchers in computational linguistics, in text analysis, and many other related areas. Today, there exist several ways to build such structures. First, it can be built manually by professional linguists. For example, this is how the most successful solutions, both in English, like WordNet, and Russian routers were built. But alternatively, it can be built using the crowdsourcing method. The crowdsourcing provides a large amount of data with high diversity at low cost. So this is exactly how the Yarn WordNet was built. And the aim of this solution was to create an extendable project available for NLP research for free. However, usually the data generated with the crowdsourcing methods needs post-processing. Due to different reasons, but the main one is that it is hard to control the user behavior during their creation and editing of the scene sets. So on the slide you can see the distribution of scene sets in length in the Yarn collection, and 65% of the data has a length less than 3. That means that many scene sets are incompleted or duplicated. The manual analysis of the rest of the data, the most important one, 63%, the length between 3 and 9, shows that the problem is much deeper. Many of the scene sets contains irrelevant words. They are mixing concepts, and because of this, they are inaccurate. The goal of this research was to design a post-processing automatic method which would receive as an input an initial scene set and would output a cleaner version of it. And a glimpse of the following with the data may be illustrated with the following example. Consider two real scene sets from Yarn. The problem with the first one is that it's actually inaccurate because it mixes different concepts. Two words are generally concept of the mother, and two words are something relative to the computers. So the first scene set must be split in two. However, after we're receiving these three new scene sets, the second one with the concept of mother is already presented in a more complete form already in the collection, so it must be merged with the existing one. And the ideal result looks like this. The performance of this merging and splitting operation might be implemented in two ways. First of all, we might somehow cluster all the initial scene sets. For example, here in 3 words would represent one cluster, and then perform a cleaning operation, or in the reverse order. During the study, we used the first method. Now about the clustering methods, them are important to briefly discuss because they lead to different results. So the greedy is a name for a single language clustering technique, and to examine how it works, consider the following example. Suppose we have two scene sets A and B which have 3 words in common. Because of this, they were merged into one. But as this new scene set or cluster, you can call it however, D has a new triple in common with a C, they were also merged, and this process continues iteratively. Opposite, we can use the triples clustering, which allows to cluster only those scene sets which initially had 3 words in common. Alternatively, we can spawn clustering using additional resources. In our case, that was a dictionary by Ludmila Babenka. This is the dictionary of synonyms. To perform the clustering, we took initial scene sets from Yarn, searched for the most similar in terms of the chart coefficient using the dictionary, and then all the Yarn scene sets which led to the same dictionary scene set compared to the same cluster. As shown in the slide, they led to different amount of clusters of the different quality. Now, quickly saying about the evaluation and metrics. As all of the methods which we'll describe are parametric, we need to somehow tune their parameters. In order to do this, we need a clean version of the data to split it in a train and test, and to collect somehow create this data. We manually created this small collection, called it a gold standard. It was made the following way. To create this, we used initial 1,000 noisy scene sets and turned them into 139 clusters in such a way that each cluster represents the synset with exactly one concept. Next, we collected it on a different metrics. But to make the training fair with respect to the models, we performed the following steps for every model. First, we are fixing the clustering strategy, and using this clustering strategy, spawn new clusters from the initial collection. Then, for every golden synset, we're searching for the closest cluster from this collection in terms of the G-card coefficient, then applying the property, the cleaning function of each model, and comparing the generated result with the golden standard using different methods. We use the training set to define the best parameters and the test set to evaluate the performance. Now we are ready to discuss the models. The first model is a word-weight, it's a baseline model. It receives cluster as an input and outputs a cleaner version of it. And how it works. For each word in a cluster, it assigns a weight. We're calculating the weight as a share of initial synset it occurs in. Consider the example of a synset with the sense of a car, and here on the left on the slide, this cluster contained about 3 or 4 synsets, and all of the words are ranked, and then we're leaving only those which are above the threshold, unless we're discarding them. And so this shortened collection represents a pure version of it. Alternatively, we can calculate not only weights for words, but for a synset. This is due to the idea that the pure synsets tend to be combined in a pure version of a cluster. And to calculate the weight of a synset, we simply take the average of word weights in it, then discarding those synsets below the threshold and operating about making a top to bottom merging from the most relevant synset with the highest weight to the least left above the threshold. The main property of these two methods is that they tend to extract the main concept, the prevalent concept in the yarn, and it follows the next results on a different clustering. However, as I discussed before, there is a problem with the multi-meaning words in the synset, and it's quite frequent. The different impact of this problem to the whole collection might be illustrated with the following example. In the first case, the synset is accurate, it's possible to use it, but in the second case, it just shows the incompleteness of the meanings available in the data, and it's quite acceptable. So we can have no splitting and still use it. But the first case makes it all inaccurate. And this leads to the idea of using the word embeddings to represent the meanings of the word as they are vectors. And probably this will help us the problem of splitting the noises. And during the study, we designed 2 embedding models. And the main property of the first model, which we call depth-to-vec, is that it expresses every meaning of the word using using the vector for its dictionary definition. The definition is about 2 sentences or less. So it's not that long. We collected them using the dictionary, but also other resources were used. And to represent the definition as a vector, we simply sum or average as a baseline method all of the words in it, all of the vectors of the words in it. And then, to perform from the cluster, the extraction from the cluster different meanings, we designed an extension of the classic agglomerative clustering algorithm. It works the following way. For every word, we get a sense vector, and searching for the next sense vector corresponding to another word. And if their similarity, in terms of the cosine similarity, above the threshold, we're combining them and continuing this process with the group, searching for sense vectors using other words. And so, as the model receives as an input a cluster, it outputs a bunch of synsets, where every synset represents exactly one meaning. And the result of the model on the correct, in the real cluster, which we got by the green clustering, might be illustrated there. The most interesting examples are 2 of them in the bottom, because the model knew really a lot of senses for these 2 words. It managed to divide and extract rare sense and a common sense. However, the quality of the model is highly depends on the amount of the meanings available in the dictionary. Still, if we have this, we are getting high results. Right now, we have some absent meanings, and there is a not solved problem with the multi-length words, for example, word entries containing 2 words. But still, we have high precision in comparison with other methods, but lower recall due to having not enough meanings. Also, it fails with the Babenka clustering due to the fact that the clusters of the Babenka tend to have the words which are represented in dictionaries by the same meaning, and that it cannot divide them into groups. Alternatively, we cannot use any definitions and directly using embeddings to generate new syntax. And how to do this? We can simply calculate all pairwise similarities between the words in a cluster, and then for each of the pair above the threshold, make the iterative process incrementally add remaining words if average cosine similarity between the word and the group exceeds the threshold, and it leads to the following results, which are the most stable cross-different clustering, but it also fails with Babenka. In conclusion, we have to say that the study is under development. We have a lot of things to try. First, we need to use the reverse strategy of cleaning plus clustering method we use this way. And for now, we're having the promising results of DAPSWAG model. There may be a lot of modifications, but it on average improves the quality of the syntax, but it still hardly deals with the hyponyms problem, which is for now unresolved how to solve this. Also, the study confirms that the crowdsourced project demands well-thought user action control and optimization. And future development is also presented on the slide. Thank you for your attention. Let's see if you have any questions.
Yes, please. Thank you for an interesting speech. I did regret one point in your topic, so it's like an explanation of question. Could you please get to the slide when you describe board wide, slide when you describe, how you form using sets based on during cluster, like
For the workplace. So, initially, the cluster consists of several synsets. Suppose we have a cluster of the synsets describing the car meaning, and let it be a length of 5. And as the word automobile appeared in all of them, it has a weight 1 because it appeared everywhere. Since the machine appeared only in 4 of them, it has a lower weight, 0.8.
Yes, so you make a using set based on most popular word in this cluster and put it to the other words to destroy that success?
We're throwing them if the weight inside this cluster is below the threshold, and the threshold is defined during the training. It is global threshold.
Okay, more questions? Please.
Just a clarification question. How did you validate your gold data set that you compared it? Like, how do you know that it's not as noisy as the original?
It's been made by our research group, which consists of the linguists, professional linguists. So there were 2 of them, and they have manually clustered these 1,000 noises by hand.
What was the agreement?
What?
What was the agreement?
The agreement was there were 2 people. And they were dealing with a separate sets of noises.
So there's no way to...
Yeah. It's a really hard task to just take the initial data and divide it in sub-meanings. Still.
Any more questions? I see no hands, so I have 2 questions. First, I'm just curious. So you are provided with a very big data set, and this data set is of very different quality. Some systems are good because they are made by those who know how to do this. They could be linguists or linguistic department students. The other could be like something messy. And I although this idea to use the gloss, the definition of sunset, to evaluate its quality was pretty cool. Isn't it? Can it be a better idea to do reversely? So, given a definition, try to gather the words again.
Ah,
Yeah, that's interesting. And it's what it did?
no, I didn't.
Okay, because I think some syntax could be really difficult to even understand what is the dominating concept. And maybe this syntax active in just and the second question is, I think I answered more. Or how? No. The second question is, how do you actually compare your approach to the others?
Meaning, how do you calculate the result?
Yeah.
So I explained this. We're defining the clustering strategy, then using this clustering strategy, populate the clusters. Then, for every golden synset, we are finding the most similar to these clusters, and after this, using the cleaning property of the model to this most similar cluster, and comparing the resulted output with the golden standard. Golden standard.
And you have a very fine goal standard.
Yeah. So this golden standard is explained.
Thank you. More questions? More questions?